What's going on, everybody? My name is Nate. Welcome to Derived, and today we're going to be talking about one-dimensional kinematics. Okay, so just for the sake of organization, here's what I'm going to talk about in this video. I'm first going to talk about displacement, velocity, and acceleration, and how they all relate to each other, and what they really intuitively mean. And then I'm going to rederive the 4 or 5 kinematic equations in 2 different ways. One kind of graphically, which has a little bit of math in it, and then also pure algebraically, which is all math. But if you stay for the ride, it's actually not that hard of math, and you can actually follow it through pretty simply step by step, as long as you can do algebra. So there's no calculus or anything in this video. I also just want to say that this stuff is hard, and if you're encountering it for the first time and you're really struggling, don't worry. It took me a long time to get this stuff, and you're going to get it too. As long as you put in the work, do some practice problems, it's really going to be simple. And speaking of practice problems, I'm going to be posting a lot more of those, so you can see this derivation video and then go right to my other practice problem videos if you want to keep going. So let's get right into it. Okay, so let's first talk about displacement. And I feel like the easiest way to visually understand displacement is picturing yourself driving in a car that is on a highway that can only go north or south. So I'm going to represent that using a number line. And all a number line is a line with a bunch of numbers on it that designates some specific quantity regarding our problem. So in this case, our number line is in units of displacement, which can typically be written as meters, feet, inches, centimeters, angstroms, whatever you want. But for the sake of our case, I'm just going to use meters. So I'm going to visually represent our car using a blue box. Here's our car. And the beautiful thing about a number line in all these kinematics problems is we can designate our origin of our number line wherever we want. We could say that our car goes on a journey and it starts at x equals 5 meters. We could say it starts at x equals -4. But for the purpose of a lot of problems, where the problem starts, the initial position of whatever you're studying, you want to designate it at x equals 0, because it makes the math work out a lot easier in the end, which you're going to see. So let's say our car starts at x equals 0, and it goes on a trip. It goes on a trip to x equals 5, and we'll label this leg of the trip A. Pretty nice. And then let's say our car turns around and goes to x equals -10. And we'll label that leg of the trip B. Okay, so how far did the car travel during the entirety of this process? And it's pretty easy to figure out. You can kind of just intuitively understand it, but I want to go through the nitty-gritty of this. So the total distance traveled, I'm going to store that in a variable that I call D for distance. During part A of the trip, we went 5 meters. Okay, D equals 5. And during the second part of the trip, leg B, we went 5 plus 10 meters. Okay, so that's 15. So the total distance we traveled is 20 meters. Not too hard, right? And as you can see, I didn't really pay attention to the negative sign because distance traveled is just distance traveled. How can you go -5 feet? Doesn't really make any sense. You know what I mean? So now let's talk about how this differs from displacement. Well, displacement has a very simple formula in physics. I'm going to call displacement delta x, and this delta literally just means difference, so subtraction in math. So delta x, which means displacement, is equal to your final position on the number line minus your initial position on the number line. And the thing about displacement is we now have to worry about the negative sign. So let's do this out. Well, our final position is just -10 meters. -10. Minus, what's our initial position? Well, it started at x equals 0, so 0. So our total displacement is -10 meters. The units are the same, but the value is different. That's the weird thing about this. And for the sake of most of these kinematic problems that you're going to be attempting, you are worrying about displacement. Okay, so now let's talk about velocity, but first I need to erase this. Okay, so now I'm going to explain what velocity is. And you probably have a pretty good understanding of what velocity is. And the way I like to illustrate it is if you picture yourself in a car just going one direction on the highway at a constant speed. Okay, so the speedometer needle is not moving, it's staying at one speed, and you're on the highway. What would that look like on the displacement graph? Well, every second you move, you get a little bit further, and another second passes, and you go that same distance because you're going at the same speed. So I think our graph would just be a straight line for displacement. Every second you move, you get a little bit further. This shouldn't be curved in any way. This shouldn't be a flat line. This should just be a straight line pointing up. So velocity is the rate of change of displacement. That's like the fundamental definition of velocity. And whenever you hear rate of change in math or physics or any branch of science, you should be thinking of units. The word per, meters per second, length per minute, feet per second, miles per hour. These are all rates of change. And the way you can intuitively understand what a rate of change is by the slope of a line. So the slope of every point on this line is equal to the velocity at that moment. So what would that look like in terms of mathematics? So we're going to define average velocity, and I'll talk about why that's average velocity in a second, equals the slope. Okay, well, slope is just rise over run. Y equals mx plus b, simple line stuff. But where are we even evaluating this from? We need some ticks on our graph. So tick 1, I'll say initial time t sub I. It can be anything you want. Typically it'll be t equals 0 because that makes the math a lot easier, but in this case I'll generalize it to some random variable. The math always works out. To some final time t sub f. And I'll draw some dashed lines to help us know where that is on the graph. And the displacement at these specific times correspond to where it falls on the y-axis. And we'll just call this initial displacement x sub I, final displacement x sub f. Just variables, placeholders for any number we want. So if we actually calculate what average velocity is using the slope formula, we find rise to just be this length, and run is just this length. Well, isn't this length just xf minus xi? This length is xf, this length is xi. If you subtract them from each other, you get this length. So let's just write that down in terms of math. xf minus xi. And isn't the same true for this distance, the run distance, the length of time? tf minus ti. Okay, well, we can condense this equation a little bit by just saying average velocity equals delta x over delta t, where delta x is just the change in x and delta t is the change in time. So I just condensed these variables into one variable just to make it look a bit neater. So is there a way we can figure out what the velocity graph is from our displacement graph? Well, yes, there is. Since this is just a line and it has the same slope over the entire graph, and velocity is just the slope of displacement, well, that means velocity would be constant during our car ride. And that makes sense because I said in the beginning, our speedometer needle isn't changing. So now let's talk about why it's just average velocity rather than instantaneous velocity or any other special kind of velocity. So let's say we have a function like this, and we define our time interval to be here, and here, our initial displacement, and our corresponding final displacement. Well, if we just follow our equation that we already derived, the slope between these 2 points, rise over run, our slope would just be a line in between our 2 positions on the plot. So the slope of this line is our average velocity, but our actual velocity during our displacement function, which is represented by the blue line here, is the slope at every single point. So our slope of this function is always changing. That's why this red line is just considered average. You're kind of waving your hand saying, okay, I'm going to average the slope in between these 2 dots and call it a day. Instantaneous velocity would be the slope at every single individual point, which you won't learn how to do until you get to calculus. Okay, so what if we start with a velocity graph and we're not given our displacement graph? Is there a way for us to go backwards? We figured out how to go from displacement to velocity, but can we go from velocity back to displacement? Now, I know you know that this constant velocity yields a straight line, but pretend you don't know that. Say we just start with this. And say we're on some time interval, t sub I, our initial time, t sub f, final time. Is there a way for us to go from this function back to this function just using math in our brains? Well, let's rewrite this equation in terms of just xf. So let's rewrite this over here and see what happens. V bar equals xf minus xi over tf minus ti. Let's multiply both sides by tf minus ti because we're trying to isolate xf. Tf minus ti, tf minus ti. These two quantities canceled, and we're just left with tf minus ti times v bar equals xf minus xi. And one last step, we're just going to add both sides x sub I, which yields xf equals xi plus v bar times tf minus ti. This is our little equation right here. This equation should look a little familiar. It's literally just the equation of a line. Y equals mx plus b, where m, our slope, is our average velocity, which we discussed a minute ago. Xi is our y-intercept, or how far up and down it is on our displacement function. And tf minus ti is just our independent variable, time. Something else is kind of bizarre about this, and it's not just the fact that it's the equation of a line. Isn't this just equal to this area? Let me show you what I mean. Average velocity is just this distance, and tf minus ti is just this distance right here. Okay, so we're kind of figuring out that if we want to go from velocity back to displacement, it's somehow related to the area under the velocity curve, which is kind of bizarre. So we know that if we want to go from displacement to velocity, it's somehow related to the slope at every single point on our displacement graph. And if we want to go backwards, it's related to area under the curve. Now, you don't have to fully understand this yet. It's just kind of something interesting to note. So just for the sake of continuity, let's graph this. We have a straight line, as predicted before. And I have one more thing I want to tell you before we move on to acceleration. We can define average velocity in one more equation before we move on. Now, I want you to pay attention to the word average. Anytime we have an average in math or physics or whatever, we're adding a bunch of things together and dividing it by the amount of times it happens. So we can also define average velocity as the initial velocity plus our final velocity divided by 2, because we have two velocities. I know that doesn't really make a ton of sense, and the first time I saw it, I got a little frustrated because I didn't fully understand it, but this is one of those equations that it's just helpful to really think about for a while and convince yourself that it's true. But don't shoot the messenger. Let's move on to acceleration. Okay, so now let's talk about acceleration. Now, acceleration is kind of interesting because it's to velocity the same way velocity was to displacement. So remember how when we graphed our displacement curve, the slope of every point on that curve was the velocity value at every point, at every time? Well, the slope of every point on the velocity curve is the acceleration value at each individual time. So let me show you what I mean. For the sake of all these problems, we're going to have constant acceleration. So we're not going to go any step higher than acceleration, which would be jerk. That comes in much harder physics courses way down the line that you don't have to worry about yet. So let's just plot constant acceleration. And from here, we're going to get our velocity equation and then our displacement equations, and then we're going to be done. So this is the beginning of my graphical derivation. So let's plot constant acceleration. Constant acceleration looks just like that. it's just a straight line. For every moment in time, acceleration is the same. So in this case, average acceleration is the same as regular acceleration. And you don't have to really understand that yet. It's just kind of interesting to point out. Let's actually define what acceleration is. Acceleration, in terms of velocity, is change in velocity divided by change in time. Okay, so this looks very similar to our velocity equals change in displacement over change in time. It's just a step further. And if I break this down even more, this is equivalent to my final velocity minus my initial velocity over my final time minus my initial time. And for the sake of this derivation, I'm just going to call this delta t, because I don't want to keep writing that. So now we want to get our velocity equation from our acceleration equation. Okay, so since we want to get our final velocity equation, first I'm going to rewrite it. A equals Vf minus Vi over delta t. Nice and pretty. Let's rearrange this equation and multiply both sides by delta t. Delta t. Of course, these two cancel, and then we have Vf minus Vi equals A delta t. Not too bad. Let's move this initial velocity to the other side. Vf equals Vi plus A delta t. Cool. So we have our velocity equation in terms of our acceleration, time, and our initial velocity. So let's plot it. So I'm going to plot this velocity function, and you're going to find it's very similar to our displacement function that we looked at in the very beginning. Velocity versus time. Okay, just like our displacement function from the beginning, this is literally just the formula for a line. Notice how it looks very similar to y, our dependent variable, equals mx plus b. So this is just going to look like this function. A linear line going straight up with two arbitrary initial and final velocities. And what you're going to find is once we have these final kinematic equations, we can just use these variables in every single problem and just plug in the values for them. It's really easy. But we also need our initial time and our final time. This is confusing. Let me erase that. I'm just going to rewrite this function over here so we remember it, because I'm about to erase all this stuff. Okay, so now let's write down the definition for velocity again, average velocity, and see what we can find about displacement. Okay, so remember that our average velocity is literally defined as our final displacement minus our initial one over delta t. We've done this. We're comfy with this. And remember how when I rearranged it, it looked like this. And if you recall, this was the area under our velocity curve on our time interval. So what I'm literally going to do here is calculate the area under our velocity curve to get our displacement function. And it gets a little mathy, but like I said at the beginning of this video, as long as you have algebra under your belt, you could do this. It's really okay. So let's literally calculate the area of this curve. I'm going to switch to a different marker. And the way I'm going to do this is partition this into two different shapes. We have our triangle and we have our square. And I'm going to call this A1, area 1. And I'm going to call this A2, area 2. So our total area, which is just represented by this, is just A total, which is literally that, equals A1 plus A2. Okay? Shapes, not too bad. What's the formula for a triangle? It's just base times height divided by 2. Our base is this interval right here, which is represented by TF minus TI. this distance minus this distance, which is just this distance, and that's just delta t. Delta t times our height, which is just vf minus vi, so this length, divided by 2. That's our A1. And let's add it to A2, which is just base times height, which is delta t times our initial velocity. So we're literally figuring this stuff out using geometry. So let's write our function so far in terms of this equation. xf equals xi plus our area under that curve, which is this. I'm going to bring the 1/2 out. Vf minus vi. I'm literally just rewriting this stuff. Vi delta t. I switched some of the variable order because it looks nicer this way in my opinion, but you can derive this however you want. And the thing we really want to encourage here is the acceleration variable into our equation, because we're going to find our kinematic problems to have acceleration as a variable a lot, so we want acceleration in here. So how can we put acceleration into this equation without screwing everything up? Well, we can take this vf minus vi and note that if we rearrange this equation, stick with me, these two equations are the same. And this vf minus vi is equal to a delta t. So we can just say a delta t is equal to this and plug it in and see what happens. xf, our final displacement, equals our initial displacement plus, I'm going to move this first because that makes more sense to me. I delta t plus, okay, here's where I'm substituting this in. 1/2 vf minus vi is a delta t times our delta t. So that's literally just delta t squared. And this, you guys, is the cake. This is what we've been working for. This is one of the big kinematic equations. And you're going to have to use this equation and get familiar with it, but I promise you it's not that bad. So I'm going to move this equation somewhere else on the board and clean all this up because we're going to do a little bit more math. So to get my final kinematic equation, I want to get rid of this delta t dependency. I want a kinematic equation without a time dependency on it because that's really helpful. And get rid of this annoying graph. And of course, put this in a pretty little box. Nice. Okay, so all I'm going to do is manipulate this equation to get rid of the delta t. And the way I'm going to do that is I need a different equation to plug in for delta t through substitution. So what I'm going to use, since I don't want to get rid of my acceleration variable, that's very important here, is I'm just going to use the definition of acceleration. A equals vf minus vi over delta t. Again, learn this, not too bad. So let's isolate this for delta t. Multiply both sides by delta t. Of course, these cancel, and we can rewrite this as a delta t equals vf minus vi. Divide both sides by a. If you're good at algebra, this might be annoying you, seeing me do all the steps here, but it helps me, and I feel like it's going to help other people in the audience, so bear with me. A's cancel, and we just have, so I'm going to rewrite this over here so it makes more sense. Delta t equals vf minus vi over a. And all I'm going to do at this point is substitute this delta t into this equation. So let's see what happens. xf, just rewriting this equation, equals xi plus initial velocity times delta t, which is this, vf minus vi over a, plus 1/2 a, plus 1/2 a, delta t squared. a squared. Okay, this looks disgusting, but I promise you it's all going to collapse at the end. Math has a way of doing that sometimes. Let's rewrite this. xf equals xi plus, I'm just going to FOIL this initial velocity in, vi vf minus vi squared over a. This just multiplies with the numerator of this. The denominator stays untouched, which is why it looks this way. Plus 1/2 a, and this is where it gets a little bit gross, just bear with me. We have to FOIL out this numerator. So what we're going to end up getting is vf squared minus 2vf vi plus vi squared all over a. Okay, this is looking even worse, but again, bear with me. It's going to be fine. Okay, I'm going to use a different color now. So what I'm going to do is I'm going to split this fraction into two separate fractions because it's easier to subtract them in the end, and I'm going to split this into 3. So let's start. xf equals xi plus vi vf over a minus vi squared over a. So these two are the same as this. Makes sense. Plus 1/2 a vf squared over a squared. That's these two terms. Minus, because of the minus sign. 2vf vi over a squared plus vi squared over a squared. Okay, one last disgusting step. So I'm going to multiply this 1/2 a into all these. Final displacement equals initial displacement plus vi vf over a minus vi squared over a plus a vf squared over 2a squared. Literally just multiply them in. Numerator times numerator, denominator times denominator, minus 2a vf vi over 2a squared plus a vi squared over 2a squared. Okay, this is the worst it's been so far, but check out what's about to happen. We have two a's on the bottom, one a on top. A over a times a. One of the a's cancels, one on top cancels. 2 over 2, that cancels. That a cancels. Exponent, cancel, cancel, cancel. Everything is canceling. This is great. Let's rewrite. xf equals xi plus vi vf over a minus vi squared over a plus vf squared over 2a minus vf vi over a plus vi squared over 2a. This term and this term are the same, except one's subtracting, one's adding. So they go away. Oh, that's nice. Let's rewrite. xf equals xi minus vi squared over a. I'm just going to write this one next. Plus vi squared over 2a plus vf squared over 2a. I'm going to erase the red because we don't need this anymore. And let's write our next step in red back up here. Okay, this is one of our final steps. What do we notice about these two guys? Let's just look at negative vi squared over a first for a second. Okay, anytime with a function, anytime with a variable, you can always multiply it by 1 and get the same thing back. That makes sense. So can I multiply this by 2 over 2? 2 over 2 is just equal to 1. That's like saying negative 2vi squared over 2a. These are the same. So let's use this instead of this negative vi squared so we can add these two quantities together, give them the same denominator. That's all I did here. So we have xf equals xi minus 2vi squared over 2a, this guy, plus vi squared over 2a plus vf squared over 2a. Okay, now we can add these two together. Negative 2vi squared plus vi squared is just negative vi squared. Let's rewrite. Xf equals xi minus 1 vi squared over 2a plus vf squared over 2a. Now we could be done. This is a perfectly good equation, but I want to put it in the form that your textbook probably says, so everything makes a little bit more sense. So let's just solve for vf squared. Let's move these two terms here and keep the vf squared here. I'm just going to rewrite it first. Vf squared over 2a equals xf minus xi plus vi squared over 2a. Just move these two guys over there and put this on the left side. Now multiply both sides by 2a. You can do this in math. Multiply both sides by the same thing. Okay, these two a's are going to cancel, and we're just going to have vf squared equals vi squared plus 2a xf minus xi. Oh my goodness, we finally got it. We got the time-independent equation. Not too shabby. I know it was horrible. I know there was a lot of algebra, but it was just algebra. And if you know how to do the steps, you can follow the logic all the way through, and we're good. And remember, we just started with our definition of acceleration and our definition of velocity. Not too bad. So I'm just going to rewrite this equation up top and then explain one more thing to you. Okay, so one last little thing I did was instead of saying xf minus xi, I changed it just to delta x via this equation, because that's probably what your textbook says. Okay, so that was the graphical derivation with some math to it. Now I'm going to do a different derivation. We're going to end up with the same equations. I just want to show it to you because it's good to see derivations in two different ways and see that they lead to the same thing. And this is just going to be all math. So if you're just like a mathy person rather than a visual person, this derivation is for you. So as always, I'm going to start with my definitions. So what's our definitions? I'll write our definitions right over here. Definition of acceleration is vf minus vi over delta t. Already learned that like 1,000 times in this video. And our definition of average velocity is final displacement minus initial over delta t. And of course, we have our weird equation. Average velocity is vf plus vi over 2. So to get our first equation, I'm just going to set these two equations equivalent to each other. Let's solve this for vf and see what happens. Okay, let's cross multiply. Cross multiply. That's a thing. 2xf minus xi is equal to delta t times vf plus vi, equal to delta t vf plus vi. All right, it's looking a little bit familiar. Now let's take delta t and substitute it here and see what happens. Well, delta t via this equation is vf minus vi over a. Okay, I just switched these two. You can do that. I could have multiplied both sides by delta t, then divided by a, but I skipped a step. So now, oh, of course, that is equal to delta t. Let's substitute this into here. So we have 2xf minus xi equals vf minus vi over a times vf plus vi. Okay, more foiling. 2xf minus xi equals vf squared plus VF VI minus VI VF minus VI squared, of course, all over A. These two are the same. They're being subtracted from each other. They go away. Now let's multiply both sides by A. Now we have 2A xf minus xi equals VF squared minus VI squared. And final step, let's move this VI squared over to the other side. And of course, we end with VF squared equals VI squared plus 2A xf minus xi. All right, there it is. This equation is the same as this equation. First, we did it graphically by finding the areas under the curve. Now we're doing it this way with just pure math. How fun. All right, so finally we got to get to this equation. We haven't derived it with just pure math yet. Okay, so this equation doesn't have a VF in it, but it does have a VI, an A, and our displacement values. So let's solve A for VF and substitute it in. Just really quick, from our definition of acceleration, VF equals VI plus A delta T. And all I did was just rearrange that equation in my head and put it right here. Okay, let's substitute that into this equation. What do we have? We have VF squared, so literally VF equals this, so we're going to square this. VI plus A delta T squared equals VI squared plus 2A xf minus xi. Okay, just a few more steps. VI squared plus 2 VI A delta T plus A squared delta T squared equals VI squared plus 2A xf minus xi. Let's divide both sides by 2A. 2A, 2A. We have VI squared over 2A, this guy, plus 2VI, these A's cancel, delta T over 2, these 2's also cancel, plus A squared delta T squared over 2 equals VI squared over 2A plus xf minus xi. Okay, so I know this looks a little gross, but this variable and this variable are the same. I could subtract it to the other side, but they're just going to cancel. We have VI delta T plus A squared delta T squared over 2 equals xf minus xi. All I'm going to do is just move this xi to the other side and call it a day. We have xf equals xi plus vi delta t plus 1/2 a delta t squared. And there you have it. What does this look like? This equation is just the same as that equation. So look at that. We did all math, we did a graphical method, we did an algebraic method, and now we have the same equations. So I'll write them up on the board so you can screenshot it if you need to for an exam, or you can always just look them up online. There's a lot of Google images that just have them plastered there that look really nice, a lot better than my handwriting, but I'll put them up there. Okay, so here are our main equations that we need to use for all of our future problem solving of kinematics. We have our definitions and we have some extra equations, while always keeping in mind that delta x and delta t is the difference between the final time or final displacement and the initial. So let's also go over what we learned in this video. We learned that velocity is the rate of change of displacement, which means if you were to plot displacement, every single point slope on the displacement graph is equal to the velocity at that point in time. We also learned that that's also true for velocity and acceleration. And the area under the curve of acceleration is related to the velocity, and the area under the curve of velocity is related to displacement. And I know that's kind of a lot, and you don't have to fully understand it all yet, or really ever if you don't want to, but I try to kind of just give you guys an intuition for everything I know about kinematics without using calculus or any really disgusting math. So over my next few videos, I'm going to be just tackling kinematics problems because I find it really helpful to see people who are decent at kinematics actually do them out on a whiteboard, because I find watching people solve physics problems helps me learn how to do them, and I want to give that to you guys. So definitely stay tuned for those videos and leave a like and subscribe. That would really help me out. I'm trying to go through all of Physics 1 content in the foreseeable future to make my channel, Rederived, your one-stop shop for everything physics. So thanks for watching, and goodbye.